So what were we doing right before spring break? Anybody recall? Yeah, Rob. Euler's method. And Euler's method, why did we want to talk about it? What was the point?
It's a numerical way to approximate the answer to the differential equation.
Yeah, perfect. It's a numerical way to approximate the answer to a differential equation. We're continuing our discussion of numerical methods this week. So I just want us to recall Euler's method. So in Euler's method, if we have a differential equation, dy dt, which we are going to label as a function of two variables, f of t comma y. Then, to calculate or approximate the n plus 1 y value, does anybody remember how we do that?
Y of n plus h and f of t sub n comma y sub n.
Yn plus h of times f of t and yn. And h was our step size. So how much were we moving in that t direction? But since Euler's method basically relies on drawing a bunch of straight lines to approximate our differential equation, it's going to approximate it, right? So what I want to talk about today is error. And can we bound the error? Can we get our error within an acceptable margin? I was about to say margin of error, but that doesn't make any sense. Error within the margin of error. Error within a specific tolerance. There we go. That's the word I wanted. So we're specifically going to talk about a type of error called local error. And what we mean by local error is the error when we assume the nth term is accurate. Okay? So it's only the error generated by the step we are working on versus the previous steps. Because there's going to be error in the previous steps, and that error is going to compound. But if we assume the nth term or the previous input is accurate, what error do we get? So we're not worried about that compounding error. And then we're also not worried about your computer is also adding error because it's truncating the decimals, right? So we're not worried about any of that. Just in this step, what is our error? So in order to find a bound for this error, we actually are going to throw it back to Taylor polynomials. Okay? So let's say we are given a function g of t with nth Taylor polynomial at a. So what I mean by this nth Taylor polynomial is not a term we've used, is we're only going to go out in terms in our Taylor polynomial. We're not going to look at it infinitely. We're just going to go out to the nth power on our x. And the notation we use here is t sub n of t. From multiple weeks now, does anybody remember how to calculate our Taylor polynomial? What our formula is? Like 2 months ago, and you had spring break in between. What's that first term in the Taylor polynomial?
Wait, which question are you talking about?
So we're working with g of t.
I mean, like, in cosine, it's 1.
Mhm.
In sine, that's like, x over,
Yeah. So how are we getting that? We're getting that from g of a. So it's the constant, it's what we get, this is our constant term, it doesn't have any x's in it. And then we start throwing in our x's, or in this case t's, and our factorials, right? So our next term would be g prime of a times t minus a to the first power over 1 factorial. And then this pattern is going to continue. So we have g to the nth power of a times t minus a to the n over n factorial. Okay. So notice it's not going on forever because we're just looking at the nth term Taylor polynomial. Okay. Didn't plan my boards well again. Anybody still need this board? Oh, look, turn right. This Taylor polynomial that we wrote is not going to approximate or not going to be equal to our entire function, right? Because we truncated it after the nth term. So there's this remainder, and we have this really nice theorem called Taylor's inequality that bounds this remainder for us. So that's what we're going to talk about next. So Taylor's inequality tells us the remainder which we're going to label r sub n of t, is going to be equal to g of t minus tn of t. So what is left when we take our nth term Taylor approximation and subtract it from our original function? Because there's all these terms we're not accounting for, right? So this is what is left, our remainder. The absolute value of this remainder can be bounded above, so it's less than or equal to m over n plus 1 factorial times the absolute value of t minus a raised to the nth plus 1 power, where the absolute value of g to the n plus 1 of t is less than m for all t minus a less than r for some r. Whew. A lot of fun notation there. So basically all this m thing is saying, because this was the part that confused me when I first learned about Taylor's inequality, is there is some upper bound of g, and this Hold on, give me a second. This should have had parentheses on it. I forgot to throw them on there because it's the derivative. It's not just the function. Okay. So all this is saying is the n plus 1 derivative has some upper bound in an area that we care about. That's all this is saying. And that upper bound is m. So the n plus 1 derivative has some upper bound, m, and we're going to use that in our inequality. I claimed this had something to do with local error and Euler's formula, though. And then I just went off on a whole tangent about Taylor inequality. So our next question is like, what does this have to do with Euler's method? Like, I don't know. A lot of fun things were just happening. So to figure out what this has to do with Euler's method, let's suppose our differential equation dy dt, which we said was equal to f of t comma y, has a solution phi of t. We're able to find a solution to it, we think. We're just going to say that we can. Then our first degree Taylor polynomial for this solution is T1 of t is equal to phi of T1 of Tn, phi of Tn plus phi prime of Tn over 1 factorial times, go ahead and don't write what I'm about to write. I'm going to say this is times t minus Tn. What is t minus Tn? Yeah, it's the h. There you go. You know what it is. So we're just going to replace this with h instead. Okay, that's our first degree Taylor polynomial. But this also looks a lot like what? Euler's. Yeah. This is just Euler's formula. Okay. So Euler's formula and our first degree Taylor polynomial are equivalent. So can we get an error bound from our Taylor inequality? The answer is yes. So our error, which we label as en plus 1, is going to be less than or equal to m over 2 times h squared. Where m is going to equal the max of phi double prime of t on our interval of a to b, wherever we have defined this differential equation, where we want to talk about this differential equation. So just as a learning check, let's compare this inequality to Taylor's inequality. So the reason I just have 2 is because I am looking at the, to do my Taylor's inequality, since I have the first degree Taylor polynomial, I would have 1 plus 1 factorial in here, but 2 factorial is just 2. And then t minus a is also h squared. It's all about that step size we're taking. Okay? Yeah, Rob, did you have a question? Okay. So this gives us a way to talk about the error in each step in our Euler's formula. It's one of those things that this is useful if you have the solution, but part of the problem is we're using these to approximate the solution, right? So it feels a little counterintuitive, but if you're running Euler's formula as a way to save on computation time and you happen to already know the solution, maybe you're running Euler's formula as part of a computer program to save computation time, you can go ahead and calculate this phi double prime, and then you can say, well, I want to bound my error by, I don't know, 1/1000th. What h size do I need to bound that error? So that's why it's really useful if you happen to know the solution, you can say, what h size do I need to bound my error to a certain level? Okay. Any questions?